Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. If you fold a standard piece of paper in half, it becomes twice as thick. If you fold it again, it becomes 4 times as thick. This feels completely harmless. But if you were physically capable of folding that piece of paper in half 42 times, do you know how thick it would be? It wouldn't just be thicker than a book. It would be thick enough to reach all the way to the moon. This explosive compound scaling isn't arithmetic, it's geometric. Instead of adding a step, we multiply. Today, we're mastering the geometric sequence formula so that you can map out exponential growth, interest rates, and viral spread with absolute precision. Now, before we jump in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. In geometric sequences, the transition between consecutive terms rely on a constant multiplier called the common ratio, and we denote that as the letter R. You can find this ratio at any time by taking any term and dividing it by the term right before. So let's say we have a geometric sequence. We have our u sub 1, u sub 2, u sub 3, and so on. To go from the first term to the second term, we're going to multiply by the common ratio r. So therefore, u2 is going to be u1 times r. And similarly, u3 is going to be u2 times r, which is equal to u1 times r to the power of 2. So this means if you want to get to the nth term, which is u sub n, this is going to be equal to the first term, which is u sub 1, and we're going to multiply this by the common ratio n minus 1 times. Because notice how the power is always going to be 1 less than your current position. And this is exactly the geometric sequence formula. So u sub n here is the value of the nth term. And u sub 1, of course, is going to be the value of the first term. And this r here is the common ratio. And n is the position, or the index number. So let's go ahead and take a look at an example. We have a colony of bacteria that doubles in size every hour. So what that tells us is the common ratio is equal to 2, because we multiply the size by 2 every hour. Now the initial count is 500 bacteria, so that means our first term is going to be 500. And it's asking us to calculate the total population at the start of the 8th hour. So that tells us n is going to be equal to 8. And we're looking for u sub 8. So using the formula, we would get u sub 8 is equal to our first term, which is 500, multiplied by the common ratio, which is 2. And the power here is going to be 8 minus 1. So this is equal to 500 times 2 to the power of 7, which is 128, which means we're going to have 64,000 bacteria at the start of the 8th hour. For our next example, we are given that the first term of a geometric sequence is 3. So that means u sub 1 is equal to 3. And we're told that the fourth term is 192. So u sub 4 is equal to 192. We're asked to find the value of r. So if we're given the fourth term, then that means our n here is equal to 4. So again, using the formula, we would have u sub 4, which is 192, is equal to the first term multiplied by the common ratio to the power of n minus 1. So that's going to be 4 minus 1. So we get 192 divided by 3 is equal to r to the power of 3, which means 64 is equal to r to the power of 3. So therefore, r is equal to the third root of 64, which is equal to 4. So our common ratio here is going to be 4. Now for our last example, we're given a sequence and we're asked to determine which term position has a value of 39,366. So from the sequence here, we can see that our u sub 1 is equal to 6, and then the common ratio r is equal to 3, because to go from one term to the next, we multiply by 3. We know that the last term, or the term that we're interested in, u sub n, is 39,366, and we're asked to find the value of n. So again, putting this into our formula, we get 39,366 is equal to the first term times the common ratio to the power of n minus 1. Dividing both sides by 6 is going to give us 6,561 is equal to 3 to the power of n minus 1. So here we're going to be asking ourselves, 3 to the power of what is going to give us 6,561? And through a process of guess and check, we know that 3 to the power of 8 is equal to 6,561. So therefore, that means n minus 1 is equal to 8. So therefore, n is equal to 9. Now, if you're familiar with your logs, we know that we don't need to actually guess and check. From this step, we can just go ahead and take the log of both sides, which means we get ln of 6561 is equal to ln of 3 to the power of n minus 1. And then our log rule tells us that we can pull the power to the front, so we get n minus 1 times ln of 3 is equal to ln of 6561. So therefore, n minus 1 is equal to ln of 6561 divided by ln of 3. And this is equal to 8, so we get 8 is equal to n minus 1, which means n is equal to 9. And now let's do a quick recap of what we covered in this video. We saw that for geometric sequences, we're multiplying by a constant ratio r to get from one term to the next, instead of adding. And just like in arithmetic sequences, there is this offset of 1 between the index and the power, and this is because the first term doesn't require us to multiply by the common ratio. And lastly, whenever you're tasked with identifying a term's position, or in other words, solving for n, prepare to use log to isolate the exponent. But if you haven't learned logs yet, then your only option is going to be guess and check. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below, and let us know what other sequences and series topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.